Last week, we took a trip down to Fermilab to see what was going on at the world's second largest particle accelerator. Despite the many advancements Fermilab has contributed to the particle physics community, many people have not yet heard of the facility. Fermilab was founded in 1967 under the visionary eye of Robert Rathbun Wilson. He justified the multi-million-dollar machine to the Congressional Joint Committee on Atomic Energy. Under his guidance, the first of the accelerators, a 4-mile-long ring, was constructed, as well as Wilson Hall. Wilson worked directly with the artists and architects. He even designed the telephone poles that fed power to the labs. As well as being a scientist, artist, and mathematician, Wilson was a conservationist, keeping a bison farm on the property. Both the poles and the farms are still there today. Committed to creating a place for a global community of scientists, Wilson kept the old town's original buildings for traveling scientists to lodge in called Fermilab Village. They have a large theater made of wood from the surrounding forests as part of Wilson's vision for conservation. They hold events there all of the time. Since Wilson, Fermilab has had 6 other directors that have continued his work and positive agenda. The 10 square miles the Fermilab grounds contain have bike paths, a learning center, technical centers, and many underground labs and entrances. The main structure, the Tevatron, is Fermilab's underground experimental laboratory. It's a system of high-energy accelerators. On my trip, we got to take a close look at the linear accelerator. The original system is still being used with some modern modifications. Most of the ancient machinery is maintained in the original machine shops they were produced in, or new ones are replaced with custom-made parts. Most of the experiments done at Fermilab use the Tevatron to conduct the experiment to some degree, so let's take a closer look into how it works. First, hydrogen is injected into the linear accelerator, and some experiments only need that much to conduct the research on low-energy photonic beams. Next, the beam can be picked up by a booster accelerator ring, and that's all that's required for some neutrino experiments. The next 2 booster rings are used for muon experiments and accelerate the streams to near light speeds using superconductive magnets. They have many sites along these 2 rings at which the beams can collide with sensors, where most of the data is collected. From there, the data is sent to the corresponding labs on site at one of the many tech centers. Some of the most famous discoveries at Fermilab's Tevatron include the top and bottom quark, which are subatomic particles, and the first direct observation of the tau neutrino. Right now, Fermilab is under a 3-month maintenance period, but they're always making new improvements, like replacing the copper drift tubes they're currently using with new neodymium cavitation superconductive ones. Other projects they're working on include DUNE, the deep underground neutrino experiment, which we made a video on you should check out. DUNE will be online in 2020, and it should help us learn more about the strange properties of neutrinos. Fermilab's experiments are completely transparent, and all their findings are public, so I don't think they're hiding anything. It looks like Fermilab has an exciting future, and I hope to go back sometime and look into more individual experiments they've conducted over the years.